Okay, so yeah, I'm super excited to introduce Chris Manning as the next speaker, who really doesn't need any introduction whatsoever, especially how he has been among the most influential figures across linguistics and NLP field, and then deep learning as well. So he's going to talk about what happens next with the LLMs.
Thank you, Yejun. Okay, so I was somewhere between cajoled and inspired talking to a mesh about higher level thoughts about language and intelligence. So I'm going to be taking rash moves here since I decided that rather than giving all of the talk I'd planned to give here, I'm just going to cut a lot of it out and redo a talk that I gave a year ago at CFAR, which has some very speculative thoughts on language and intelligence, and that might be fun. So we'll see how that goes. Okay, but let me sort of tell the big picture of the talk that you're only going to see part of. Something that I've been working on quite a lot with various people, including student Eric Mitchell, who'll be looking for a job, and Chelsea Finn, is the idea that if we're going to do more with language models, that a language model is like a car engine, but to actually have a car that you can drive around, you need all sorts of things apart from the engine. You need wheels, but you need safety measures like seat belts and airbags, and you need all sorts of other conveniences to make it possible. And there's tons and tons of interesting work in what's needed for an ecosystem of tools around language models that make them effective and safe. So we know that large language models are fascinating, extremely good. They should have lots and lots of practical use cases, but in practice, they also have a lot of problems and societal issues. So there's problems with keeping them up to date as the world changes. There's problems with getting correct, consistent, non-hallucinated answers out of them. There's problems with their use in society when people are unhappy with the undetected use of large language models. And there's problems with having them interact in appropriate ways with human beings. And so I think the situation we're still in at the moment is kind of like this. So Bloomberg fairly recently trained a pretty good large language model, Bloomberg GPT. They trained it especially on financial data and got good results from doing that and showing it works much, much better on financial data than other large language models. And the question is, what are they doing with it? And to a first approximation, the answer is they're doing nothing with it because they still regard it as too risky to let loose in any customer-facing application because who knows what it might say at the wrong moment, which is a pretty serious issue if you're a company like Bloomberg. So the only people who are actually using Bloomberg GPT at the moment is researchers inside Bloomberg. And I think that's a sort of a fairly large issue for a lot of us. So we want to be working on how to put in place this kind of guardrails, safety measures, and guidance that allow safe use of large language models. And I was going to present 3 pieces of work to that topic, but I'm going to make this up as we go, and I'm going to show the last one first, which is talking about a new way of getting language models to learn from human feedback. And we'll see how long that one takes, and then I'll either switch straight to the speculative part or maybe show a second thing. So let's go to this one. Okay. Yeah, so this, oh, no, that's not the right one. That's not the one I wanted to go to. That was the second one. Okay, so in this part, what I want to present is direct preference optimization, which is a new algorithm for learning from human feedback. So you can think of it as an alternative to the conventional kind of reinforcement learning from human feedback that's been so central to all of the large language models that are in use today. So as is well known, pre-training large language models on bulk text does not naturally give a language model that responds to user intent. So that you give it something like, this is a bit small, I guess, explain the moon landing to a 6-year-old in a few sentences, and a GPT-3 model would just decide some random pattern to explore, and maybe it says explain the theory of gravity to a 6-year-old, explain the theory of relativity to a 6-year-old in a few sentences. What we'd like to get is models which understand questions and instructions as things to respond to, that gives us the kind of performance that came out in the world with ChatGPT. And well, how can you do that? Well, the pioneering method to do that was this method of reinforcement learning from human feedback. And so let me just briefly go over the pipeline of how that's done. So there were 3 stages. So the first step is still general. Well, you start with a general pre-trained large language model trained on your trillion words of internet text. And then what you're going to do first is supervised fine-tuning, which is simply doing more training to predict the next word as you had before, but you're now training it on a particular kind of text. So you've collected text that is responses to human-generated demonstrations of instruction following tasks, and you fine-tune it to be better at following that kind of text. So now you have something that sort of knows how to respond to questions and instructions. So the second step is we then sample answers from the instruction tune model, typically 2 continuations for each instruction, and then we ask for feedback from human evaluators. And then the final step is tuning the language model to human preferences using reinforcement learning. This is now what's widely referred to as aligning your AI. Personally, I'm not actually that fond of that term, but it's commonly used. Okay, so let me say that in just a little bit more detail as what you do, starting with the step 2 part. So the feedback is you have a prompt, 2 possible answers sampled from your pre-trained and supervised fine-tuned model, and then you collect the human preference as to which one of the 2 is better. So I'm going to use the notation where X is the prompt, the YW is the preferred response, the winner, and the YL is the dispreferred response, that's the loser. Then the preference model is assumed to follow the Bradley-Terry model, so that there's some kind of score that can be given to each pair of a prompt and a response, and then you're predicting the goodness by then sticking that into the difference into a logistic function, and this gives a binary probability.
Just like ELO and chess?
Sort of. I mean, it's a little bit different in its basis to ELO, but
okay.
Yeah, it's sort of similar.
Yeah, it's the same model, but it goes back to the early 50s.
But wait, so I had another question. Like, would you regard these 3 components as just logically separable from each other? Like, you could do some without doing others?
I mean, yeah. I mean, so supervised, I believe in theory, the supervised fine-tuning should just be eliminable and it would make no difference to how well it would work out. Though in practice, supervised fine-tuning is a cheap way to get your language model in the zone so you can collect good data from which to start collecting the rewards. So if you didn't do the supervised fine-tuning, you need 100 times, 1,000 times, I don't know, way more reward data and to do way more of the reinforcement learning. So, that's why that's there. As I will discuss more in some of the experiments, the supervised fine-tuning by itself just isn't enough, that doesn't get you where you want to be. So you definitely want the later phases. And then they're sort of separate, right? You're training your reward model, and then you're doing the reinforcement learning based on that model. And what I'm going to show is a different approach, which more couples those 2 together. Okay, so what we do then is we train the reward model. So the reward model is going to be a neural network, so it has lots of parameters. In particular, the standard thing is the reward model is basically just a language model. So the standard thing you do is you take a pre-trained language model and you lop off the very top where the softmaxes are to produce words, and you stick on a single additional fully connected layer, and then you train that, and that is your reward model. So you're training this reward model as a neural network to minimize negative log likelihood under the assumptions of this Bradley-Terry model of rating preferences. Okay, so finally then we get to step 3. So we now have our parameterized reward model that represents goodness according to humans in terms of responses. And so what we want to learn is a policy which will achieve a high reward. And the way we're going to do that is we're going to start with initial parameters, sample from the policy, and then trying to optimize over that policy to produce a high reward. And standardly, people then always add this second term of wanting to keep the model that you're learning close to your original model, because all the preference data that you've collected is on the original model. So if you're wandering too far away from it, it's then very unclear what you might do. So you want to keep the safety of your language model. Yeah, so I'm not really much of a reinforcement learning person. So, you know, in my head, what I'm always thinking to myself is really this is basically a language model with a fully connected layer on top. And this is also a language model when you're running these things in these systems. Okay, but crucially here in what you're doing in this process, it's offline reinforcement learning over the preference data you collected in the second phase.
And what's parameterizing the space of possible policies here?
A transformer with an extra fully connected layer on top.
So for each such question, the answer is another transformer.
2 quick questions. One, do the reward functions transfer? If I get a reward, if I learn a reward function for one particular model, is it going to transfer to another language model? Or I learn a reward model rather, is it going to transfer?
So the reward model should transfer, right? Because the reward model is just having produced a model of what do humans prefer. So you should be able to take your reward model and use it in the reinforcement learning phase with any language model.
The other question very quickly, you've said a lot, you know, you do this, you do that, or this is what is done. How standard is this?
I mean, I think this is what everybody does. So this was the process of InstructGPT that was pioneered at OpenAI. Similar stuff then happened at Google. You know, like there's some people have played with variants a bit of sort of different reinforcement learning methods, but you know, I guess what InstructGPT did work so successfully that my impression is basically everyone has copied it with pretty much this recipe. Okay. Yes. Oh. Yeah.
You mentioned that the reward model is just a pre-trained model with then another layer on top. Like, so does that mean like?
But you train the whole thing, so it's not frozen.
So when you get like the pre-trained model, like it's from the, so you originally just start with the pre-training and then branch it out into a simple model.
Yeah. So that's short answer is maybe yeah. That's a part where there's some variation and some fun and games that people can do. I mean, because sometimes people don't fully separate them. They actually keep the low levels of the language model shared. So it becomes a sort of funny kind of multitask learning, but maybe we can kind of leave out some of those details here and just think that you can either have multiple copies or you could use different language models. It doesn't even have to be the same one. Okay. So then you go into the reinforcement learning stage. So the standard thing that people have used is PPO, because that's what John Schulman did at OpenAI, and it seemed to work well. But in general, you're wanting to use some actor-critic reinforcement learning algorithm. So just sort of like 2 weeks ago, this paper came out on secrets of RLHF and large language models, part 1 PPO. And this is I think this is the kind of diagram that you provide if you don't want people to understand anything more when they finish the paper when they started. And I'm not going to go through this diagram. What I'm hoping you'll take away from this diagram is, although PPO can achieve good results, it's actually pretty complex. It's potentially unstable for some elements of its design, and it takes lots of computational resources to be running it. So what I'm hoping to tell you about today is this work that a bunch of us have done recently at Stanford on coming up with a more straightforward, we hope, alternative called direct preference optimization. Okay. So that was the background. Is everyone roughly good on the background? Yeah. Okay. So the idea of direct preference optimization is that if we parameterize our reward model correctly, differently, we can extract the optimal policy from our learned reward model with no additional training, i.e. we don't have to do the same kind of actor-critic reinforcement learning process. So we don't have all of the complexity from that previous diagram. And so rather than the traditional reinforcement learning pipeline that's been used in RLHF, where you collect the preference data, based on that you train a reward model by maximum likelihood, and then you do this iterative process of sampling completions from your model, scoring them with the rewards, and then sort of trying to use PPO to improve how well you perform, that we're going to have a direct correspondence between the reward model and the optimal policy. And because of that, we can have this much simpler process where we just have preference data and then do a maximum likelihood learning process to get our final language model. And our final language model will indeed be the optimal language model relative to our reward function in a way that I will explain as we go on. And so the question then is how we can go about doing that.
Sorry, getting the optimal model, does that also include minimizing the distance from the model you started from?
Yes. Yeah, so that's part of the optimization. Okay, so we start with exactly the same RLHF objective as before. So yeah, here's the answer to your question. Same objective, we're wanting to maximize, so so for our data set, preference data set that we've collected for each X, and then drawing Y's from our policy and working out its reward. We want to maximize the reward, and then subject to this same constraint of wanting to stay close to the base model. Okay, note that this expression works for any reward function, so it doesn't have any requirement that it's connected to our PPO. So it turns out that in general, just given the expression above, you can work out in closed form an optimal policy for the reward function. So this was something that was actually shown by people in Sergey Levin's group up at Berkeley a few years ago. And it's not actually that difficult. You do a sort of the usual bits of algebra and math and introduce, your z's and 1-on-z's, and you can rearrange it into this form. So the optimal policy is proportional to the base model, weighted by some function of the reward. And remember that our base model PyRef, that's our large language model that's been fine-tuned with the supervised fine-tuning. Okay, the problem here is we've still got this Z term, which is the sum over every possible response to your instruction. And so this is makes it a valid probability distribution, but makes it not possible to just go ahead and compute it because it's intractable to work with exactly. And that's something that we then sort of work out a way to work out our way around. So doing an even more trivial bit of algebra, you can just rearrange this so that you want the expression for what the reward is. And so the reward is then going to be beta times the log of the ratio of the probability of the optimal policy over the reference policy plus beta times the log of the normalization term. And so this ratio is positive if the policy likes the response more than the reference model, and negative if the policy likes the response less than the reference model. Okay, so this is our general reparameterization. And so it's sort of giving us the expression for the reward function that a policy is optimal, the reward function that a policy is optimal for can be expressed as a log probability ratio between the policy and the reference model plus some function. I mean, here the normalization term Z is still intractable and does depend on the reward function, but it's only a function of the prompt. It's not a function of what we generate. And so the key idea of DPO is we're going to train our policy such that the reward function that is optimal for, given this equation, agrees with human preferences according to Bradley-Terry. I mean, so in other words, we're just going to stick this equation into the Bradley-Terry loss. So we have a loss function on reward functions, a transformation between reward functions and policies, and that's going to give us a loss function on policies. Okay, so here's our Bradley-Terry loss model of human preferences. Here's what we just produced as the reward as a function of the policy. And then we just plug those two things together. And now we have a loss function that we can evaluate in terms of policies. And here, the very nice thing happens that these two terms are the same and they cancel out when you subtract them. And so now we've gotten rid of the nasty Z term. So that's cool. And so the train model this will give us a train model which will have a policy that will be optimal for the reward function that aligns with human preferences. So the model that optimizes the DPO loss is the optimal model, minimizing the Bradley-Terry loss. So the only thing we've effectively changed is we have a different architecture for the reward function. And so once we do normal reward learning, we'll be able to extract the optimal policy in closed form. So one thing that you could worry about is, well, we've sort of changed the architecture in terms of neural terms or the form of what we're working with. So is it possible that the way we're expressing the reward model in terms of the language model somehow affects what kinds of rewards we can learn? And so the clever students proved some theorems showing that under fairly mild assumptions that all reward classes that are consistent with Bradley-Terry losses can be represented in terms of this reparameterization of the reward in terms of a ratio of policies which are themselves language models of the kind that we're using here. And I'm not going to go through that either, but you may find it in section 5 of the paper. Okay, but what I will show you is some experiments. So here's just some URLs of code. This is our own implementation of this. But a nice folk at Hugging Face have already released a version of it that appears in their Transformers Reinforcement Learning Library. So the first experiment is a kind of a toy experiment. So this is generating synthetic text to give a very positive movie review. So we've got IMDb movie reviews, and we're going to use as the prompt the first handful of words of the movie review, and we're going to say, generate more text, and we want you to write a very positive movie review, no matter what the first 5 words say. And for the reward of the movie reviews, we're going to use an off-the-shelf sentiment classifier. So our gold standard and what we can use as a reward model is this pre-trained sentiment classifier. And so we then use that pre-trained sentiment classifier to judge between pairs of generations when doing reward training. And then we can compare optimization with either PPO or DPO. And in the PPO case, we also consider both at learning the reward model from the preference data or just using the gold reward model, which is given to us by our sentiment classifier. And so this then compares a whole bunch of results. So where these results come is from each method, we did 4 training runs, and we stopped it at various checkpoints. And so for each of those things, we could see how high is the average reward it's getting for the generation and how far away the learned policy is from the starting off language model. And so if we sort of start at the bottom, so one thing you could do is just use the data of what is the preferred forms and do more supervised fine tuning on that. So you're sort of learning that the positive examples are good. And that's where really this just isn't very effective, that you sort of basically, no matter how near or far you are from the reference language model, you're getting a reward of about 0.6 in green. Then the next thing we did was running the Hugging Face Transformers RL library, running their implementation of PPO, and that's somewhat better. It's starting to learn a better average reward of almost 0.8 as it moves further away from the reference model. Playing around with this sum, we sort of found that the Hugging Face PPO implementation, or at least the hyperparameters and schedules that it came with, not really the core code, didn't actually seem that great. So we fiddled around with PPO some. And so for our version of it, we're then into this one, and it's learning much better. It's getting up to about 0.9 reward usually, though it sort of starts to trend down over here in a couple of samples, which maybe I'll come back to later. Now, both of these are just using the supervised model, the gold standard for the reward as the reward, and not actually learning the reward. But then for these pinkish ones here, we're doing the sort of the full standard pipeline. We're both learning the reward from the preference data, and we're running the PPO algorithm. And that behaves basically exactly the same, maybe fractionally better over here. Then the final line here is unlikelihood training, which is an algorithm that's been proposed and in a way is not completely dissimilar to the method that we use in DPO, in that you're wanting to, be the good stuff is being made likely, the bad stuff is being made unlikely, but it doesn't have the same kind of scaling of examples that's used in the DPO method. And so then over here, and also it's quite unstable, right? Sometimes it works great and sometimes it works much less well. Then up here is the DPO examples. And so where you'd like to be is up in the top left corner. You'd like to get high reward, and you'd like to not have the language model move too far away from the base language model, because, as a language model, something that produces language just like humans do, the base language model is essentially perfect, right? It's the one that's this extremely well calibrated probabilistic model. And so you're able to get extremely high reward without moving very far away from the base language model. And its performance is extremely stable. It doesn't vary much between runs.
Do you have a sense as to why unlikelihood training is unstable? I would have thought that if I'm remembering correctly, you're just increasing the probability of the good stuff and decreasing the probability of the bad stuff. There's no RL, so I wouldn't have expected it to be unstable. I know that's not what you're actually giving the talk about. I'm
Yeah.
just curious if you have any insight.
I'm not really sure if I do.
I wonder whether the unlikelihood, at least your implementation, does anything about the KL term, which maybe helps to stabilize the learning. In the original unlikelihood, you may not be doing KL term, and I don't know whether you necessarily added it on.
Yeah, I think I have to all sort of pass on that one too, as I'm not 100% sure. But I think maybe the other part of it is the unlikelihood training does not provide the same kind of weighting over examples as to which examples are important to modulate how you change the parameters. And that might be much less stable, because in DPO, you're sort of feeding things into the logistic form of the Bradley-Terry loss, which means that sort of there are examples where you learn a lot, where you want to differentiate between things that are apart but not too far apart. And there are examples where you learn very little once you're into the sort of flat parts of the logistic. And I think that might be part of it as well, but not 100% sure. Okay, so can we do slightly more real-world experiments than that? Yeah, so this experiment is on Reddit TLDR summarization. So you're starting off with a prompt of something. So this is sort of embedded in one of these experiment frames of, you know, which of the following summaries does a better job at summarizing. Here's the post, here's summary A, summary B, give a judgment. But the prompt is the thing to summarize, you know, as some Reddit post, I've been ungrateful to parents who've only wanted the best for me for the longest time. I'm so lucky that I have the life I have, but I have squandered it. I'm 17, leaving for university, and I've had an epiphany, blah, 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 blah. And so the job of both of these models is to summarize this post, and DPO came up with, I've been a shitty child and I want to make up for it. What can I do for my parents on their birthdays and Christmas to show them how much I love them? Now, you know, we're not actually explicitly in the algorithm comparing the output of DPO and PPO, but, you know, here's just a fun example where we did it with PPO as well. And PPO said, I've been a shitty person to my parents. What can I do to make it up to them? That part's very similar. Before I go, and what can I do after university to make them happy? And what can I do to make them happy after university, if that is the case? And so then we wanted to judge which one of these things, when we had two answers from the same model, were better. And what we used to give judgments primarily was GPT-4. Very scalable, modulo the money. And GPT-4 said about these two, summary B, which is the DPO one in this case, because they'd be randomly ordered, more effectively captures the main points of the post by focusing on making the parents happy through gestures on special occasions, while summary A seems repetitive and less clear, preferred B. And so here is sort of what we're going to do here is we're going to compare the summarization win rates of different learned policies, learned RLHF models, compared to human written summaries using GPT-4 as the evaluator. And one other parameter we can vary for generation, which has already come up, is the temperature at which we're doing generation. And optimal temperatures vary somewhat with methods, though it seems like for the RLHF methods, generally very low temperature, the sort of fairly deterministic one seems to perform worse. So certainly for PPO, it performs pretty well at low temperatures and really falls away at high temperatures. DPO performs better than PPO, which is why I put the slide up, of course, but it also falls away less badly. This best of 128 is sort of a crude but effective method, which is you generate 128 different possible answers, you score them all by the reward model, and you just take the best one. So if you run sort of best of for a large enough K that actually proves to be a quite effective method of finding a good answer. Let's see, this is the base language model. We were using GPT-J, and simply using supervised fine-tuning again doesn't work very well. Okay, so that makes it look good. Of course, this is, oh, sorry, I should have said, this is against human written summaries. So anything above 0.5 means that GPT-4 is preferring the model's output to the human summary. And so we have the better than human summarizers here, since a lot of these results are getting about 60% being chosen by GPT-4. Of course, you might just worry that GPT-4 is a very bad evaluator. So we did a smaller study that then looked at humans. So this is taking two of the models, DPO, and then one of the poorly performing ones, the supervised fine-tuning. And it's comparing both of them to PPO at 0, which also performed well, and saying, what win rate do you give to these models? And so supervised fine-tuning mostly loses to PPO, but DPO, according to GPT-4, won 54% of the time. It's a little bit better at temperature 0, but the human said that DPO won 58% of the time. So from this, it seems that humans and GPT-4 ratings are fairly similar, and if anything, the humans seem to slightly more prefer what you're getting out of DPO. It's also the case, this is sort of that a human agreeing with GPT-4 is, again, basically the same with humans agreeing with each other. So that it seems like, basically GPT-4 judgments seem as good as human judgments in this circumstance. One more real-world example. So Anthropics released this helpfulness, harmlessness data set where the prompt here is I'm trying to locate the residential address for J.B. Pritzker and heir of the Hyatt Hotel fortune. And, the harmless answer is to say, naughty, naughty, I'm not meant to be telling you the private addresses of famous people. And so we were evaluating on that data set. And again, we're comparing to sort of a human one and looking at our win rates. So again, we're able to see that we're able to get about a 60% win rate from DPO on this data set. We actually weren't able to get PPO working on this data set, so I can't compare it against PPO, but I've got best of 128, and it's certainly, again, working much better than preferred fine-tuning. So just one final point on this is, an empirical phenomenon that's been noted is that at some point, if you keep on optimizing your award and doing your PPO, so PPO learned reward model, you tend to get to the point where that it thinks the reward is continuing to go up, but according to the true reward model, actually your performance is going down. So that's been noted in this alpaca farm paper by some of our Stanford colleagues. It's also been replicated in synthetic settings at OpenAI. And so you might thought that we'd suffer worse from that problem because after all, we've come up with this clever reparameterization so that you're actually completely optimizing the policy for the reward. But it's actually, we can't say that wouldn't happen eventually, but it just doesn't seem to happen badly. To the length that we've done fine-tuning for quite a while, that you're not seeing anything sort of falling away badly. Okay, so DPO allows you to express the reward model simply in terms of the language model itself. And so you can fine-tune the language model on preference data directly without having to do this kind of iterative reinforcement learning training loop. And so DPO gives a simple, apparently quite stable, and computationally much cheaper way to do reinforcement learning with human feedback. And it's optimizing the same kind of objective and performs very well. So make your life simple. Try using DPO when you want to fine tune from human preferences. Okay, so that's the end of that. And I'll now switch horses and say my very speculative part on language. Here we go. Okay, this talk is these slides are at this point historical, since I gave them in October 2022 at a CFAR meeting. So crucially, the thing to remember, which is really hard to remember these days, is ChatGPT is less than a year old. In fact, it's just coming up for its 9-month anniversary in a few days' time. So ChatGPT had not yet come out at the time I gave this talk, since it came out about a month and a half later. So it's not going to have the very latest examples about it, but let me mainly for sort of 10 or so minutes concentrate on the high-level part. So what I want to do is sort of introduce this idea of a von Humboldt machine, the idea that we're sort of moving into this phase of neural networks that use symbols and language to build their intelligence. It's a purely speculative talk, but hopefully good for thinking here. So my dear colleague, Jan Lacoon, and Jake Browning, a philosopher, have been involved in writing a sequence of articles for the journal Noema. So the first one they wrote was what AI can tell us about intelligence. And, you know, I really, really like that one. It clearly and balancedly, in my feeling, contrasted, you know, the two main views of symbols as whether they're hard-coded at the outset, which is kind of a Chomskyan view of language and intelligence, or whether they can be learned through experience, and it argued well for the latter. And so I said, I like that, hey. But, you know, a few months after that, they produced another piece in Noema, which was called AI and the Limits of Language. And that one I thought was kind of misguided. These slides are sort of my response to thoughts on reading this Browning and Lacoon piece. So these are some of the things that they say. Large language models' understanding of language, while impressive, is shallow. Abandoning the view that all knowledge is linguistic permits us to realize how much of our knowledge is non-linguistic. Non-linguistic mental simulation in animals and humans is common and useful for planning out scenarios and can be used to craft or reverse engineer artifacts. A system trained on language alone will never approximate human intelligence, even if it is trained from now until the heat death of the universe. As you can see, they have some fairly strongly held views about the limits of language. And I think they're sort of ending up sort of arguing against a false position where their claim that they're wanting to try and say is that people believe that language exhausts knowledge, that the only knowledge that exists is language, where I don't think even the strongest proponent of language would say that language exhausts knowledge. You know, even Noam Chomsky knows that when he sticks his hand under the water, it feels hot or cold, and that's not really linguistic. So I think in making this kind of argument that they actually end up as false prophets because they've sort of been too scared of all the things that Gary Marcus writes. And so it's then leading them to take a rather ridiculously strong position in reverse. Indeed, one of the sections of their paper is titled exorcising the ghost. And so that leads them to be sort of making these kind of false claims where they're failing to recognize how important language is to human intelligence. They make other false claims as well. I don't know, maybe education is very different in France. I was having a conversation with Shafis of how more rigorous education in other countries, but they claim while science classes do have a lecture component, students are graded primarily based on their lab work. I don't know what educations other people had, but I have never done a science class that was primarily graded based on its lab work. And well, I've already read. Oh yeah, and then there's this bit. They say language is important because it can convey a lot of information in a small format, and especially after the creation of the printing press and the internet can involve reproducing and making it available widely. So I think this is a very common error, and it's certainly the error of Jan Lacoon's position that he feels that the only roles of language are compressing your knowledge and allowing it being communicated to other human beings. And communication of ideas so that they're not on one individual's head but are broad spread across humanity, that actually has been an important idea that's advanced humanity a lot. And having printing and the internet, that's advanced humanity a lot. But I think there's just more to it, right? So humans and many of the elements of human-like intelligence, it's not that different from other animals, right? The things that we talk about for human intelligence, memory, planning, cause and effect reasoning, tool use, compound tool construction, all of those things are also things that are observed in animals. And, for higher animals like chimpanzees, right, their brains are basically homologous to ours. And even, areas that are the primary language areas like Broca's areas, right? Chimpanzees have Broca's areas. And so, people have observed how chimpanzees will use their tools, use their sticks to get the ants out of a hole. And then there's instruction because one chimp will teach the little chimp how to go about doing it. And if we watch the video for longer, then the other little chimp's going to have a go. So it's learning by instruction, just like human beings. But it turns out you don't need something as clever as a chimp. You can have something like with a microscopic brain like a crow. In particular, all of these experiments are done with Southern Hemisphere crows. I think somehow Southern Hemisphere crows are more intelligent than Northern Hemisphere crows. I'm not sure of the details of that. But, crows in the Pacific, really, they can do all the same stuff that you can stick food in holes. The crow can't reach it with its beak. It can go off and find, still not reaching it. It can then find a stick, and then it can get bits of food out with its stick. It puts the stick down. It realizes it won't balance, so it puts its foot on it. It's planning ahead. It understands all of this stuff, right? So, kind of intelligent, but, we sort of have this difference that the limit of tool use by animals is sort of a few crude sticks, and we human beings have rather better tools. And so Wilhelm von Humboldt was this kind of interesting German dude. He's who American grad schools is essentially attributed to, the idea that was invented in Germany. But he mainly worked on language. He's a favorite of Noam Chomsky's, who always quotes his statement that human language must make infinite use of finite means. He's used that as the justification for the kind of universal grammar that he's worked on. But he said a lot of other things. People can find lots of things in Humboldt's writings, including some quite racist things, actually, which I won't get into today. But one of his central ideas was that language is not merely an outward manifestation of thought for the purpose of communication. So one of the things he said is language is not product, i.e. ergon, but an activity, energeia. And so effectively he distinguishes from what we tend to call now it's sort of system 1 cognition from system 2 thinking. And he sort of saw language as an essential part of being able to extend the mind to allow system 2 thought. So mental activity which produces the expression of thought, this is this higher system 2 thought, is always directed upon language already given. It is not purely creative, but a reshaping activity, and that language is the necessary foundation for the progress of the human mind. We can debate how totally true that is, but it sort of seems to be true. So Daniel Dennett, in his book From Bacteria to Bark and Back, that it's primarily about consciousness, but in the course of that book, he introduces sort of 4 levels of intelligences. And so this is getting to levels of intelligences that we're talking about in the morning. So the lowest level is Darwinian, which is your pre-designed fixed competence doesn't improve in your lifetime, so that you only get improvement by evolution. So that's things like bacteria and viruses. Then the next level up is Skinnerian intelligence. So that's when you can do reinforcement learning, the classic Skinnerian rewards, and learn to get the rewards. The third level of intelligence is then Popperian intelligence. And so Popperian intelligence is when you build a model of the environment. And so then you can do offline testing of plans with your environment model. And it seems like already crows can achieve this level of Popperian intelligence. And then the 4th level that Dennett distinguishes is Gregorian intelligence. And Dennett argues that the essence of Gregorian intelligence is that you can build tools that magnify your thinking. So language is one tool that magnifies your thinking, but Dennett argues that other tools that magnify human thinking include mathematics, computers, but also democracy, that democracy has been a way of building a tool to improve our thinking. And Dennett argues that human beings are the only biological examples of Gregorian intelligence. And so what it seems like we're doing now is that we're seeing in these recent language models that we're now starting to have machines that have Gregorian intelligence, that they can build their own tools. These examples now are kind of old because they're in the InstructGPT era, but precisely once we started doing the instruction fine-tuning, rather than just seeing sort of arbitrary completions from GPT-3, we can have language starting to be manipulated as a tool inside these models. I might skip a few of the other examples because they're getting old now. But you know, what we're starting to discover now is that we can sort of do so much with these language models by regarding them as building and using thinking tools. An interesting guy who's become a sort of a hit sensation on the internet lately is this guy, Riley Goodside, who's sort of become the prophet of how to write complex prompts which get your models to do wonderful things. He's got an interesting history. He used to work at dating sites. He used to work at OkCupid and Grindr, but now he is the sort of the true prophet of how to prompt your large language models to do interesting things. And so the kind of, oops, sorry, I have this bit here. The kind of thing he's worked out how you can do is, you are GPT-3. If you can answer directly, use this format. If you're not able to answer, what you should do is consult IPython. Use this format to send stuff to IPython and then get the answer. And so this kind of complex instructions and use of tools, you then build up enormously what you can get your language model to do, because it can call out to IPython and then it can multiply numbers completely correctly. So, you know, for most of the history of deep learning and its resurgence, you know, people believed that gradient-based learning was the answer to everything. And the question was, how to extend that to higher forms of cognition. But I think that's actually maybe now seeming wrong, that gradient-based learning is the right answer for type 1 cognition. But to really reach type 2 cognition, maybe the right answer is constructing Gregorian thinking tools. And effectively, some of what we're now seeing at OpenAI elsewhere is the construction of Gregorian thinking tools, where the language model is then making use of a calculator or calling out to some other device. And so we're entering this world where language is a mechanism of instruction, but also a mechanism of thinking. And thinking over symbolic language actually enables higher level thought and a form of cognitive improvement in the same way it has for human beings versus chimpanzees and crows. Thank you.
Super interesting talk. I have a question about the DPO, which seems to assume that the preference data is all given a priori. So it's a more offline, whereas DPO, I presume, can be more online. So depending on the quality of the preference data that DPO began with, I wonder if there can be difference empirically. So when you say it's optimal, I suspect that it has to do with some assumption about the preference data that you're given.
Yes. Yeah. Sure. Right. So perfectly good. Yeah, that's a perfectly good objection, is to say, well, wait a minute. Yeah, that there are some advantages to really doing reinforcement learning. And so you are right. But as I understand it, the way everyone is doing RLHF, they're doing it based on offline reinforcement learning, where here's the big pile of preference data, learn on that. And so, if you remember, your opening reinforcement learning lectures where you've got the agent wandering around in the little micro world and it learns as it's going, that's not actually what they're doing, right? They've just got this training set and they're saying, let's run a reinforcement learning algorithm on it. But you could feel that, yeah, well, wait a minute, as you're sort of learning and veering away, if you can then be collecting more on policy data, then that would help you. And yeah, that's possible. It's not what's standardly being done. I guess the question then is, whether you can get the kind of preference data to go with it, right? Because at that point, there have been two possibilities. One possibility is, well, maybe you can get some value with unsupervised on policy reinforcement learning. And maybe that could be a possible strategy, but it's not very clear whether that's going to work at all, since it really seems like the contrast of learning between having good and bad has driven all of this. But otherwise, this has only become relevant if you are somehow collecting, here are two possible responses, which one do you like more, human? Maybe kind of like in web search results. I mean, of course, to the extent that you collected that data, you can then also put in a pile for further offline reinforcement learning.
Yeah, thanks. This is a really interesting talk. Just kind of thinking about this last stage with kind of thinking tools. If I think about, say, like how we built computers, it seems like to build a computer, we had to build kind of all these other engines of production. Like we need to mine silicon. There's kind of all these like economic, just like physical tools and like building stuff we have to do that maybe isn't showing up in language models right now. And so I'm wondering if you think that stage is also important, and if so, how it kind of fits into this picture.
Yeah, I haven't really thought about mining silicon, but I do believe that we need stuff that isn't language models. I'm with you, Jan Lacoon, insofar as saying, oh, we should actually have decent models of the 3D world. I mean, I think we're at an interesting point right at the moment, right? So basically, lots and lots of roboticists are now making use of large language models in their robotic system. And that's because of the crazy reason that once you move outside of just sort of the things that a traditional physics engine can do, you know, movement with rigid objects, that language models are actually a better world model than anything else anybody has. But, you know, on the other hand, they're really lousy world models in sort of the details compared to the kind of, I think, you know, 3D world understanding that we have. So, yeah, I think there are a lot of other things that you need as well. But, you know, part of that is learned and shared through language, right? Yeah.
Thanks for the awesome talk. Just a small question. One is, if we ensemble the results from different temperatures, would PBO be comparable to DBO in terms of the ability?
Not sure, to be honest. Maybe.
Another
I mean, the temperature is sort of a separate parameter. I'm not quite sure how to
it fluctuates over the temperatures, and then DBO it turns more stable. Yeah, so it would be nice to see the empirical comparison to this. Another question is the multimodality. Would that add on any explanation or description to the language on human thought?
Sure. I mean, so I think this is, I mean, I think most humans have the intuition that all the other stuff of what they've seen and smelt and felt is really, really important. I mean, you know, I think in terms of what's happened in the last 5 years, the surprising thing has been in the other direction. That is, I think, blown our minds as to how much you can do with language alone, because it turns out that even for things that seem very physical, there's just lots and lots of language you can find in books, web pages, etc., that talk about the feels of things and describes what they look like, and you can do an amazing amount of language-only reasoning. But, you know, it's still just very incomplete. So, yes, sure, we need to also have more.
So maybe just one last question.
So the question was, is there something like a halfway point towards Jan's position, where he also believes in RL or interaction with the world is kind of important? And do you think that something like RL is also an important component of actually teaching a language? Not just for conversation, but like also for intelligence.
I mean, so yes, I do. Yeah. So, I mean, it's hard to know this for sure, right? Because, I mean, you know, I think it's just been unexpectedly good what you've been able to achieve with huge language models trained on 1 trillion plus words. You know, I think all the theory of child psychology and human language acquisition says that just shouldn't be possible, that interaction is clearly just hugely, hugely important for human development of both language and cognition. You know, but it seems like somehow it turns out that if you instead substitute, well, you know, we're now up to about 100,000 times as much data as a little human sees, that you can do a very good job of learning without interaction. I guess the question is that still fundamentally upper bounded in some way?
Or if you know of any experiments that show that interaction improves.
Oh yeah, well, I mean, for humans, there are tons
No.
of for language models, and yeah, I think it's not quite so clear, right?
Okay, so it seems that we have to take the rest of the questions offline, but let's